Solve some lead code today. So today we have lead code 295, that is find the median from data stream. Basically in this problem we have to create a data structure that can handle a stream of data. So the stream is simply adding numbers. So first I add 4, then I add 3, then I add 2, then I add 1. That's the simple stream. And this data structure should also be able to give us the median of the entire data that is currently present in the stream. The median is the middle value in an ordered integer list. What it means is that we can have a list like 1, 2, 3, and it is sorted, right? It is from smallest to the greatest, and then here the middle element is going to be the median. So this is the median. But if the size of the list is even, there is no middle value. The median is the mean of the two middle value. What it means is that if we have a list like 1, 2, 3, and 4, the size is even, right? And here we don't have any middle value. We have two values in the middle. So we will take them 2 and 3. We will add them and then we will just divide them by 2. So it is basically equal to 5 divided by 2, that is 2.5. That is the median. One thing to notice is that we can find median in a sorted list, okay? But the stream will have random values. First you can get 3, then you can get 2, then you can get 1. So the sorted order is not guaranteed by the stream. The stream can give you any random number. So how can we solve this thing? Well, first of all, let us try to find out the median. So the median only needs the middle values, right? And finding the middle values is very easy in case of list. So even if you increase the size of the list, we can always find the middle value just by taking the length of this entire array and dividing it by 2. So that will simply give us the middle element or middle two elements, whatever we want. So that is going to give us an order of 1 time complexity, which is pretty good. Like this is exactly what we want to find the median. The tricky part is actually inserting the elements in the list. So suppose that in the data stream we get 3 first. So okay, we will add 3 here. Then we get 2. Now what do we do here? Well, we can simply add 2 here, then actually run a sorting algorithm on this list. Okay, so this will actually sort this to 2 and 3, and then our insertion will complete. Then we will get 4 here. Then we can simply add it at the 4 here, right? Then we can get 1 here, right? And as soon as we get 1 here, 1 will be placed here, and we will end up sorting this entire list again. So now we will run a sorting loop here. So we will get 1, 2, 3, and 4. So one way is to just add the element in the list and run a sorting algorithm in the list. So that is one way to do this. And this will make the time complexity of our insertion function to be order of n log n. Why? Because sorting takes order of n log n. That's why it will become order of n log n. But you can do better. There is more efficient ways. So if I get 3 first, I will place it here. Then if I get 2 here, then I will not place it here. I will not do this, right? I will simply take the 2 and I will go through this entire list. I will see where is the first element that is greater than 2. So I will find 3 and I will take the 3 from this position. I will shift it to this side. And then in the position of 3, I will insert 2. And this thing we can always do. Now if we get 4 here, then we can simply come here. We will go through the entire list and we will place the 4 at the last, right? But if we get 1 here, we will come here. We will see that 2 is greater than 1. So we will take the 2, we will take the 3, we will take the 4, we will shift it to this side. And then in the array, we will have something like 4, 3, 2. We have shifted them and then we will get an empty place here that was occupied by 2 earlier. And then that's where we will place 1. So in this solution, we are going through the entire list, right? All the time. So it is going to take order of n time complexity because we are just going through the list, we are shifting elements and we are just inserting it. So this is a linear time complexity algorithm. But to make this solution pass on the LeetCode, you have to do even better. Order of n will not cut out. So in order to do better, we need to understand how does the sorted array works. So suppose that we have 1, 2, 3, 4, and let's just say 5 also. So if I want to find the median, I can simply take the middle element. Right, this is the median. I can get the length and I can divide it by 2 and I will get the index of this element and I can get it in order of 1 time complexity, right? But if we really look at it, what we are really doing is that we are dividing the length of the array or the list by 2. What it means is that we are dividing the array or the list by 2, right? We are dividing it in the half or trying to divide it in the half. And so we will have 2 separate sections. One will be this section and another one will be this section. And then we are taking the maximum value from this section. Right, so the maximum is 3, so that's what we are taking as the median, and we are doing this when the length of the entire list is odd, right? Odd means we will actually have a middle element and we can find it. But what if it was even? We can have 1, 2, 3, 4, 5 and 6. What will we do in this case? We can again take the length of the list, we will divide it by 2 and that will divide the list by 2 from here. we will again have two sections, this one and this one, right? In this section, we want to find out the maximum here. And in this section, we want to find out the minimum value, right? So from one section, we want to find out the maximum. From another section, we want to find out the minimum. And then we will take these two values and then we will simply add them. So 3 plus 4 divided by 2, and this will give us the median. So 7 by 2 is equals to 3.5 or something, right? So 3.5 is the median. So this gives us a hint that we want the maximum from a particular section and we want the minimum from another section. And we want to make sure that finding the maximum and the minimum is order of 1 complexity, or at least as low as we can get. And in this kind of situation, we can use a data structure like heap. So heap is a data structure that gives you the maximum or the minimum element that is present in the list. So if you have the max heap, it will give you the maximum element. If you have min heap, it will give you the minimum element. If you want to know how heaps work, I have already created a video that you can look at, because heaps are a very simple data structure and they are really useful. So we know that we will have an array or a list and we will divide it by 2. Okay. So what we want to do is, instead of having a single list, we want to do is we will have two lists, or basically two heaps. One will actually be a min heap and another one will be a max heap. Now we know that the list is actually divided like this. We want the maximum from this section and we want the minimum from this section. So what it means is that we will store 1, 2, 3 in this section and we will have a max heap here. So this will be a max heap because we want the maximum element from these elements. And then we will store these elements here, 4, 5, 6, and it will be a min heap. Why? Because we want to get the minimum element in the least time complexity. So instead of having one single list, we will actually have two heaps, and these heaps will actually help us to find out the median. To find out the median, we can simply take the max heap and we can get the maximum element in order of 1 time complexity, and then we will take it here, and then we will have the min heap and we will get the minimum element in order of 1 time complexity, and we will get the 4 here. We will add them divided by 2, we will get the 3.5 in order of 1 time complexity. Now the question is, how do we insert elements in these heaps, right? So suppose that we will get an element like 4 first. So we will take the 4 and we will insert it in the max heap first. We will not insert it in the min heap, we will insert in the max heap. And right now the length of the max heap is 1 and the length of the min heap is 0, right? So the difference between the max heap and the min heap can only be 1 at max. If it is greater than 1, well, that is not correct. Why? Because ideally we would like the max heap and the min heap to be equal to each other. Okay, their length should be equal. But we know that we have a case where we can have odd number of elements. So we can have 1, 2, 3, 4 and 5. And if we divide this list, we will get 3 elements in the max heap and we will get only 2 elements in the min heap. But this case is also valid, right? Because we have a middle element and we want to return it. So that is why the maximum difference between the length of max heap and min heap can only be 1. If it is greater than 1, we will have to do something. We will see what we need to do later on. But now that we have inserted 4 here, we can move on. Okay, now we will try to insert, like just say 3. And I want to take the 3 and I will place it right here. Notice that I have not sorted it. Okay, I have placed the 3 right here. But now as you can see that the length of the max heap is now greater than the min heap. So what I need to do is I need to take out the maximum element here. Okay, so I will take out the 4, and taking out 4 is simply order of 1 time complexity because we are using heap. So I take out the 4 and I will place it inside of the min heap. So I will place it here, and insertion in a heap is basically order of log n. Simple as that. So it is not order of n, it is order of log n, which is very low time complexity. So whenever the difference between the length of max heap and min heap is greater than 1, that is 2 or 3, then you will take the element from the heap that have more elements and place it in the heap that have less elements. Right now max heap had more elements, so we placed it inside of the min heap. So 4 is no longer here. Now let us try to add 1 here. So I will take the 1, I will place it here in this place. Length of max heap is 2, length of min heap is 1, and the difference is simply 1, so it is fine. Now we will take another element, like just say, I don't know, 5. Okay, and I will take the 5, place it right here. And now the length of max is 3, length of min is 1, right? So 3 minus 1 is equals to 2, and this is not okay, right? So now we will take the element from the heap that have more elements and we will place those elements in the heap that have less elements. So right now max heap has more elements, and so we will take the max element from the max heap, that is 5. So 5 will be taken out in order of 1 time complexity, and then we will place it inside of the min heap. So 5 will come here, and this will take order of log n time complexity. Now let us move on and add 2 here. So if I take the 2, I will end up inserting it in the max heap first. So I will have 2 here, and then I will check the length. So the length of the max heap is 1, 2, 3. It is 3, and the length of the min heap is Well, 2. So the difference between them is 3 minus 2 is equals to 1, which is okay. We can accept this. And now that we have inserted all the elements that we wanted to insert, if we want to find out the median, what we can do is we can simply take the max heap, find the maximum element, that is 3 here, and then we will take 3, and we will take the min heap, find the minimum element, that is 4 here, and we will take the 4 and we will add them and divide by 2 if we want to. But since the length, okay, the length right now is 3 and 2, so 3 plus 2 is basically odd length, so we will not do this. Okay, we will simply take the element from the max heap 3 and we will return it as median. And actually there is a simpler way to do this. If the length of max heap is greater than the length of min heap, so right now it is 3 and it is 2, so we will simply take the element out of max heap and we will return it as answer. So right now we will take the 3 and return it as answer. If the length of min heap is greater than the length of max heap, we will take the element from the min heap and we will return that. But if both of them have the equal length, then we will take an element from the max heap, then we will take an element from the min heap, we will add them, we will divide them by 2 and then return that as answer. Simple as that. So now that we understand the answer, let us look at the code. Now here is the code. First of all, we are initializing the object with small list and large list. Small list will be the max heap, so it will contain all these elements. Why? Because they are the smaller elements. These elements are actually smaller than this element. And the large heap will actually contain this section of the element, that is 4, 5, 6, which means large heap will actually be a min heap and this is actually a max heap. The names may be counterintuitive. We have max heap for the small one and the min heap for the large one, but the logic that we discussed earlier does not change. So we have initialized the list and now we have these functions, add number. So during insertion of element, we are taking the number and we are pushing it in the small heap first. And the reason I'm using -1 is because you have to multiply the value by -1 in Python and then store it in the heap to actually make a max heap, because Python does not implement the max heap by default, so you have to use this hack around to actually use a min heap as a max heap. This is a very Python specific thing. You don't have to do this in other languages. So now that we have placed the num in small heap, we can move on. Now we have to check a few things. If there is some element in the small heap, there is some element in the large heap, and the element at the small heap is actually larger than the element at the large heap, we will pop the element from the small heap and place it in the large heap. The reason we have that kind of condition is because suppose I want to place 100 in the list, okay, or maybe 1,000. I want to place 1,000 in this heap. So I will take the 1,000 and I will place it inside of this heap, the max heap right here, okay. Now the length of this max heap is what? It is 3. The length of min heap is what? It is 2, right? So it means the difference between their lengths is 1, okay? So it means we will not actually take out any element and place it inside of the min heap. We will not do that, right? But if we really look at it, we have 1, 2 and 1,000. We have 4, 5. So if we try to look at it in a sorted way, so we will have 1, 2, 4 and 5. And then we will have 1,000 in a normal list, in a normal sorted list, right? And then if we will try to find out the median, we will take the length, that is 5, and then we will find the median, and then we will find the middle element, so it will be 4, and this will be the answer, right? But in this case right now, if we check based on the previous logic, then we will see that the length of the max heap is more than the length of the min heap, so we will take out the element from the max heap, right, the maximum element, and that will be the answer. So in that case I will just end up taking out the 1,000 and I will say that 1,000 is the median, which is clearly wrong. And that is because the 1,000 was supposed to be in this section, right here. And that is because the 1,000 was supposed to be in this section, not in this section, right? But since we are adding everything in the max heap first, and then we are checking for the length, and then we are dealing with the other logic based on the length of these heaps, in this kind of situation we will actually keep these kind of very large elements in this max heap, but they should not be in the max heap, they should be in the min heap, right? And that's why we will always check if the largest element in the max heap is actually larger than the smallest element in the min heap. We know that we need to take that largest element out and we have to place it inside of the min heap. So that's what that condition is talking about. Now once this is done, we are checking the other conditions. If the length of the small list or the max heap is actually greater than the length of the large list or the min heap by 2, we are adding +1 to make sure that the difference between them is not just 1, it is greater than the 1. So if the difference between them is actually greater than the 1, we will take element from the small heap or basically the max heap, and then we will push it inside of the min heap or basically the large list. And the same condition is copy pasted right here. In case the min heap have a greater length than the max heap, then we will pop from the min heap, that is the large list, and we will push it in the max heap, that is the small list, to make sure that we will get the right answer. Now one thing to take care of is -1. You need to make sure that you are multiplying -1 in the right directions if you are using Python. If you're using some other language like C, C++, Java, or C Sharp, you will have the concept of max heap there. But since we don't have max heap here, that's why we have to use this hack, okay, to actually use a min heap as a max heap. So you need to make sure that you are actually using -1 in right places. So you can look at the code right here and see where I'm using the -1 and just try to understand why I'm using it. Because multiplying by -1 is a Python language specific issue. It is not a DSA problem. Now here we have the next function, that is find median, and this is the simpler function. So if the length of the min heap, that is the large list, is actually greater than the length of the max heap, that is the small list, then we will simply take the element from the large list or mini heap, because we will have the odd element with the extra element present in the large list or the mini heap. Now if the things are other way around, that is if the max heap or the small list have greater length than the large list or min heap, then we will take out the element from the small list or basically the max heap, and we are multiplying that by -1 to make sure that we are returning a positive value, because small list or basically the max heap will be having negative values inside of it. This is a Python specific thing. Else, if the length of both heaps is equal, then we will take out one element from each of the heaps and we will add them, and then we will divide them by 2. Here I am multiplying -1 with the small list because this small list or the max heap will have negative values inside of it. So getting an element from this small list will return a negative value, and we will need to multiply it by negative to make the entire result positive here, and then we can add it to the other element and then divide by 2. Now here I can simply divide by 2 and it will give me a float value, that is decimal point values. But if you're in other languages, then you will need to use data types like float or decimal or basically double or some other kind of data type to make sure that you are getting point values. Otherwise, you will simply get integers, which will actually make your entire answer wrong. Because as you can see that we can have 2.5, that is a decimal or floating point value, as a median also. So keep the data types in mind. So now let us try to run this thing and see what happens. So yeah, it runs in 196 milliseconds, beats 46.45% solutions on Leetcode, and passes all of the 22 test cases. It's a pretty efficient solution. So now let us look at the time and space complexity for this particular solution. So for insertion of the element, we will have the time complexity as order of log n, because we are using heaps. We are just taking out elements from the heap and inserting in the heap, and insertion and deletion from the heap actually takes order of log n time complexity. That's why we have order of log n here. The space complexity is going to be order of n because we are going to have two heaps that are going to store all the elements on the stream. So if the stream have n elements from 1 to n, then we will end up storing n elements together combined in both the heaps. So eventually taking up order of n space complexity when both of the heaps are combined together. Now for finding the median, we have the time complexity as order of 1 because we can take out the elements from the heap in order of 1 time complexity, and the space complexity is also order of 1 because even if we have the same length for both of the heaps and we take out 2 elements, this entire operation will take at max 2 extra variables, right? And 2 extra variables are always going to consume the same amount of space no matter how many elements are present in the heap, because we are only going to take 2 extra elements always. So this extra space does not depend on the input size, which means no matter how many elements we have in the list or in the heaps, this particular space will always remain constant, that is fixed, and that is why we have order of 1 space complexity, that is constant space complexity. We are using constant space complexity for this operation. So yeah, like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, just let me know in the comments. Now we will meet in the next video. Till then, bye.